Hello everyone. On this video we will be taking a look at linear approximations and differentials. Okay, so to start off, to kind of come up with our formulas for those, I just want you to remember your point slope form. Let's say y minus y1 equals m times x minus x1. Your point slope formula. Okay, so what if we let f of x be differentiable at a point x equals some value we'll call c. Okay, so in other words, it's differentiable at some point c and f of c. Okay, so if this is your ordered pair, this would be your x1 and your y1. Okay, and we know that your slope is your derivative at that point. So your y minus y1, we're going to rewrite it. So y minus y1 becomes y minus f of c equals your slope at point c, so that's f prime of c, times x minus x1 or x minus c. Okay, so we're going to go ahead and solve for y, so we're just going to add f of c to both sides. So y is equal to f of c plus f prime of c times x minus c. Alright, so instead of y, we're just going to make it a function of x. So let's say you have some function that we'll call capital L of x is equal to f of c plus f prime of c times x minus c. Okay, so this is your linear approximation. And sometimes it's called your tangent line approximation. I guess depending on who you ask and which textbook you're looking at. Alright, so using the same approach, let's say if we have our xy axis here, so this is your x and this is your y, and let's say you have your graph there. Let's say this point here is an x, and this point here is some value c. Okay, that will make this point also on your y-axis your function of x, and this point here would be your function of c. Okay, so the difference between this x value and this c value is literally your change in x. So dx is your change in x. And same thing here, from this y value to this y value, your change in y is your dy. Okay, so if we go right back to this formula here, y minus f of c is equal to f prime of c times x minus c. We see that our change in y, or your y value, f of x and f of c, that's literally just your oops, sorry about that, dy. So that's your change in y. You have two different y values. Okay, so that's equal to f prime of c. Okay, that's just your derivative at any particular x value. Okay, and x minus c, that's literally just your difference between x and whatever this x value is here. So that would just be, I don't really need the parentheses there. That's literally just your change in x. And this is the formula for your differential. Okay, so another way you can also come up with this formula without having to go through all that is if you know that y equals f of x, and we also know that derivative of y with respect to x equals f prime of x. Multiply both sides by dx, and you end up right back there. You have dy equals f prime of x dx. So it's just another way to come up with the very same formula. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and jump to our first example. Okay. All right, so let's say for example, what if we let y equals x squared? Okay, want to find your dy when x equals 1 and your change in x is equal to 0.001. All right. So when you see you're going to solve for dy or your change in y, basically they're telling you your differential of y formula is going to be used. Differential of y formula. Okay, and that's change in y equals f prime of x dx at x equals c. Okay, so the only thing missing is we have to find our f prime of c. Okay, so need to find our f prime of c. Okay, because at x equals 1, that's x equals c, so all of those will become c. Okay, so we know that f of x is equal to x squared, since that's just your y equals x squared, same as f of x equals x squared. Which means that f prime of x is equal to 2x. Which means that x equals 1, f prime of 1 is equal to 2 times 1. So f prime of 1 is just equal to 2. Okay, so using that formula, just going to rewrite it again. So that's f prime of 1 dx. Okay, so that means your dy will equal f prime of 1, which is 2, times your change in x, which is, oh, that should be 0.01. Added one too many zeros. Sorry about that. There we go. So that should be 0.01, which is 0.02. Okay, so that's your change in y, or your dy. Alright, so if you're still writing on this one, feel free to press pause, but we're going to go ahead and jump to the next example. Alright, so let's say for this example, we want you to find your change in the area, which is basically their d of a, which is the estimated change of the surface area, if the sides of a cube changes from 9 to 9.2. Alright, so to help you visualize it, we're going to go ahead and draw a cube. Okay, so start off with two squares, then just connect the lines, and we have our cube. Okay, so let's say we just shade in this front side of the cube. Okay, so this is our side, and this is the side. Of course, with a cube, all the sides are the same length. And I'll just draw a little line through my S so it doesn't look like 5. Okay, so the area of a cube is length times width times height. But the length, width, and height are all the same length. So the area of a cube is equal to 6 times S squared. Okay? Or we can just use A equals 6S squared. Okay? So the change in the area with respect to the side, we're going to bring down, it's just the derivative of that, so we're going to bring down that 2, so that's 12S. But to just solve for our change in surface area, we just multiply both sides by that ds. So our change in the area is equal to 12S ds. Alright, so we can actually find our estimated change of surface area. But the only thing missing here is we don't know what S and ds are. So we have to find S and our change in S. Okay? So we know that. Make a little side note, I'll put that over here. The sides change from 9 to 9.2. Okay, so this tells us really all we need to know. So we have our change in S is actually equal to 0.2. Since ds equals change in S. Okay, you go from 9 to 9.2, you actually changed 0.2. Okay, and we know that our starting side length was 9. Okay, so that means our change in area is equal to 12, and we're using this right here, times S, which is times 9, times our change in S, which is 0.2. Okay, So we know that equals 21.6. Nope, sorry about that. Okay, so this gives us our surface area. So the surface area is estimated to increase by 21.6 square units. Okay, we don't know if it's inches, feet, centimeters, but we just say square units of measure. When the sides increase from 9 to 9.2. Okay, so that's how differentials are kind of helpful. Okay, it helps you figure out little things like that. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example of linear approximation. Alright, so let's say, for example, actually, linear approximation, let me put the formula up here since it was a few pages back. So our linear approximation formula, that's L of x is equal to f of c plus f prime of c times x minus c. Alright, so let's say, for example, what if we wanted to find the linear approximation of f of x equals negative 7x minus 3 over 3x plus 1 at x equals negative 1, and use it to approximate f of negative 0.8. Okay, so in other words, we're going to use what we have to figure out what we don't know, basically. Alright, so using our linear approximation formula is going to equal c is equal to negative 1. That part we know. So we're going to fill in our f of negative 1 plus f prime of negative 1 times x minus negative 1. You could have put x plus 1, but I just wanted to not skip any steps. So in order for this to be useful, we need to find f of negative 1 and f prime of negative 1. Okay, so f of negative 1 is pretty easy. We just plug in negative 1 for our x values. So f of negative 1 is negative 7 times negative 1 minus 3 over 3 times negative 1 plus 1, which gives us 7 minus 3 over negative 2, which is negative 2. Okay, so we know that f of negative 1 is equal to negative 2. So to find f prime of negative 1, we have to find the derivative first. So f prime of x is equal to your denominator. So 3x plus 1 times the derivative of your numerator, minus the numerator times the derivative of your denominator all over your denominator squared. Okay, so if we finish, f prime of x is equal to, you have 3x plus 1 times the derivative of negative 7x is just negative 7. Derivative of negative 3 is just 0, so that's times negative 7 minus negative 7x minus 3 times the derivative of 3x plus 1 is just 3 all over 3x plus 1 squared. So if we go ahead and distribute, we see our f prime of x is equal to negative 21x minus 7 plus 21x plus 9 all over 3x plus 1 squared. So once we go ahead and cancel those two out, our f prime of x is equal to 2 over 3x plus 1 squared. Now if we plug in our x equals negative 1, so we know that f prime of negative 1 is equal to 2 over 3 times negative 1 plus 1 squared, which ends up being 2 over 4, or just 1/2. Okay, so we know our f prime of negative 1 is 1/2. Alright, so now we can go ahead and plug everything in to our linear approximation formula. Okay, so our linear approximation is equal to our f of negative 1, which is negative 2, plus our f prime of negative 1, which is 1/2, times x minus negative 1, that's just x plus 1. Okay, so this is our linear approximation at x equals negative 1. Okay, please excuse the shadow. The sun kind of shifts around, so you'll get a shadow every here and there. Alright, so when x is equal to negative 0.8, our linear approximation of negative 0.8 is going to equal negative 2 plus 1/2 times negative 0.8. If you wanted to do it without decimals, negative 0.8 is actually equal to negative 4/5. So you can replace that if you want to. So replace x with negative 4/5 plus 1. Alright, so that will give us negative 2 plus 1/2. Negative 4/5 plus 1, just replace that with 5 over 5, and you end up with 1/5. Okay. So adding these two together will give you negative 19 over 10 as your linear approximation. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Let me see if the focus can help on this a little bit. Alright, so let's say if we wanted to estimate. Okay, I'll try to write a little bit bigger so hopefully the glare won't affect it too much. Okay, so estimate the cube root of 26.9 of f of x equals the cube root of x about the value x equals 27 using linear approximation. Okay, so using a linear approximation, we're going to estimate this cube root, even though we know the cube root of 27. All right. So, using our linear approximation formula is equal to f of c plus f prime of c times x minus c. Remember, that's at x equals 27. Well, I guess you could say c equals 27. Okay, so it's c equals 27. Our linear approximation is going to equal f of 27 plus f prime of 27 times x minus 27. Okay, so what does this tell us? Well, it tells us that we have to find f of 27 and f prime of 27, or L of 27, and well, we'll go figure that out once we get there. But we have to find the f of 27 and f prime of 27 if we're going to solve the linear approximation. Alright, so move that up a little bit. So f of 27, we're literally just plugging that in. That's equal to cube root of 27, which is equal to 3. Since 3 times 3 times 3 is 27. Okay, so to find the derivative, f of x, actually let me put that down here. F of 27 is equal to 3. So if f of x is equal to the cube root of x, we're going to go ahead and rewrite that as x to the 1/3 power. So that means the derivative, f prime of x, is equal to 1/3 x to the 1/3 minus 1. Which is equal to 1/3 times x to the negative 2/3 power. Let me go ahead and move that up. All right. So, since that's the negative 2/3 power, we're going to make that f prime of x is equal to 1 over 3 times x squared to the 1/3 power. Because remember, you multiply those, you just get 2/3. Or f prime of x is equal to 1 over 3 times the cube root of x squared. Okay, so we found our derivative, so now all we have to do is plug in our 27. so f prime of 27 just equals 1 over 3 times the cube root of 27 squared. Okay. Now with this one, we're going to do a little bit of problem manipulation. Only because we know that 3 is equal to the cube root of 27. So we're going to replace that 3 with the cube root of 27. So it's 1 over the cube root of 27 times the cube root of 27 squared. Okay, so we can actually combine those two since the indices match. So that's 1 over the cube root of 27 times 27 squared. Which is equal to 1 over the cube root of 27 to the third power. Alright, so that means our f prime of 27, sorry about that, is equal to 1 over 27 because the index and the exponent cancel out. Okay, so f prime of 27 equals 1 over 27. Excuse me. Alright, so now we can use our linear approximation formula. Okay, so our linear approximation is equal to f of 27, which is 3. And let me clean up that 3 a little bit. Plus, we have our f prime of 27, which is 1 over 27, times x minus 27. Okay, so this is our linear approximation at x equals 27. Alright, so, well, x equals 27 formula, linear approximation formula. Now when x is equal to 26.9, that will give us our cube root approximation. Clean that up a little bit. 26.9 is equal to 3 plus 1 over 27 times 26.9 minus 27. Alright, so by the time you plug that in, you end up with an approximation of 2.9963. Which is the linear approximation of the cube root of 26.9. Okay, which doesn't seem too far off, since the cube root of 27 is 3. So that being close to 3 seems about right. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and do one more example. Alright, so let's say, for example, use a linear approximation of f of x equals sine of x at x equals pi to approximate sine of 183 degrees. Okay, and you want to give the exact answer. And 4 decimal places. All right, so what I want you to do is I want you to press pause and try to solve this one on your own. All right, so assuming you've pressed pause and you've worked this one out, let's go ahead and verify your answer. Okay, so again, our linear approximation, f of c plus f prime of c times x minus c. But in this case, c is equal to pi. All right, so we can go ahead and have our linear approximation equals f of pi plus f prime of pi times x minus pi. Okay, which means, what do we have to do? We have to find f of pi and f prime of pi. Okay, so to find f of pi, we just plug in our pi. That's sine of pi, which is equal to 0. Okay, so we know that f of x is cosine of x. Oh, f prime of x, sorry about that. Which means our f prime of pi is cosine pi, which is -1. Okay, so we know that f of pi equals 0 and f prime of pi equals -1. All right, so we can go ahead and plug those right into our linear approximation formula. Linear approximation is going to equal f of c, which is f of pi, which is 0. I guess you might as well circle this one since that's the one we're using. F of pi, which is 0, plus f prime of pi, which is -1. So instead of plus, we can make that -1. Times x minus pi. Which means our linear approximation is going to equal -1 times x minus pi, or you can distribute the 1 if you like. You don't have to. Whichever one is most comfortable for you. All right, so now to make this a little bit easier to put as an exact answer, we can get our 183 degrees and convert that to radians. Okay, so 183 degrees. Remember, to transfer degrees to radians, well, I guess you can say to convert degrees to radians, you multiply it 183 times pi over 180 radians. Okay, so really that's just 183 pi over 180, which is 61 pi over 60 radians. Okay, and that helps because you have a pi right here. So if you have a degree that you plug in, it won't really give you an exact answer. Okay, so you want to be able to combine those two pi values. Okay, so our linear approximation at 183 degrees is really the same as saying the linear approximation at 61 pi over 60 radians. Okay, which is equal to, we go ahead and plug it into this one, -1 times 61 pi over 60 minus pi. Okay, so that will equal -1. So if we have 61 pi over 60, we just make that 60 pi over 60. So now we have our common denominators. We can go ahead and finish that off. So 61 pi minus 60 is 1 pi, or just pi over 60. Multiplied by -1 is negative pi over 60. Okay, so that is our exact answer. Okay, now if you plug that into a calculator, it comes to be about -0.0524. Okay, so this is your answer to 4 decimal places. All right. So hopefully this made sense, and I will see you on the next video.